Good morning. We continue our course of formal language automata and codes. And today our lecture will be 16. And the lecture will be devoted to context-free grammar as programming languages. One of the most important uses of the theory of formal languages is in the definition of programming languages. In the construction of interprets and compare for them. The basic problem here is to define a programming language precisely, and so use this definition as the starting point for the writing of the efficient and reliable translation programs. Both regular and context-free languages are important to achieving this. As we have seen, regular languages are used in the recognition of certain simple patterns that occur in programming languages. But as we agree in the introduction of this part of lectures, we need content-free languages to model more complicated aspects. As with most other languages, we can define a programming language by a grammar. It is traditional in writing on programming languages to use a convention for specific grammars called the Backus-Naur form or BNF. This form in the essence the same as the notation we have used here, but the appearance is different. In the Backus-Naur forms, variables are enclosed in the triangular brackets. Terminal symbols are written without any special marking. The Backus-Naur form also uses subsidiary symbols such as vertical line, much in the way we bowed down. Thus, the grammar in example 5.12 must appear in the Backus-Naur form as expression, terms, expressions plus terms, terms, factors, line, terms factor, and so on. The symbol plus and the symbol star are terminals. The symbol vertical line is used as an alternator in our notation, but the following symbol, two-point equal, is used instead of array. The Backus-Naur form description of programming language tends to ask more explicit variable interfere to make the intent of the production explicit. But otherwise, there are no significant difference between the two notation. Many parts of C-like programming languages are susceptible of net definition, restricted form of context-free grammars. For example, the while statement in the C can be defined as while statements, while expression statements. Here, the keyword while is a terminal symbol. All other terms are variable which still have to be defined. If we check this against definition 5.4, we see that these look like an S grammar production. The variable while statements on the left is always associated with the terminal while on the right. For this reason, such a statement is easily and efficiently parsed. We see that reason why we use keywords in programming languages. Keywords not only provide some visual structure that can guide to reader of a program, but also make the work of the compiler much either. Unfortunately, not all futures of typical programming languages can be expressed by an S grammar. The rules for expression above uh, are not of this type, so that pathing becomes less obvious. The question then arises what grammatical rules we can permit and still parse efficiently. In complete extensive use has been made of what are called LL and LR grammars. These grammars have the ability to express the less obvious beauty of the programming language, yet allow us to parse in the linear time. This is not a simple matter, and most of it is beyond the scope of our discussion. We will briefly touch on this topic in next lectures, but for our purpose, it is sufficient to realize that such grammars exist and have been widely studied. In connection with this, the use of ambiguity take an added significance. The specification of a programming language must be unambiguous. Otherwise, a program may yield a very different result when processed by different compilers or run on different systems. As example 5.11 shows, a native approach can be easily introduced ambiguity in the grammar. To avoid such mistake, we must be able to recognize and remove ambiguities. A related question is whether a language is or is not inherently ambiguous. What we need for this purpose are algorithms for detecting and removing ambiguities in context-free grammars, and for deciding whether or not a context-free language is inherently ambiguous. Unfortunately, these are very difficult tasks, impossible in the most general sense, as we shall see later. Those aspects of programming language that can be modeled by a context-free grammar are usually referred to us is syntax. However, it is normally the case that not all programs that are syntactically correct in the sense are in fact executable programs. For the program language C, the usual Backus-Naur form definition allow construct such as chars A, B, C, followed by C is equal to 3.2. This combination is not acceptable to the language C complete since it is violates the constraint. A checked variable cannot be assigned a real value. Text-free grammars cannot express the fact that type clashed may be not permitted. Such rules are part of programming language semantics, since they have to do with how interpret the meaning of a particular construct. Programming language semantics are a complicated matter. Nothing as elegant and coincide as context-free grammars exist for specification of programming language semantics. And consequently, some semantic filter may be poorly defined or ambiguous. It is an ongoing concern both in programming languages and in formal language theory to find effective methods for defining programming language semantics. Several methods has been proposed, but none of them has been universally accepted and are as successful for semantic definition as context-free language have been for syntax. So I finished my lecture. Thank you for your attention. I wish you good luck, good health, and please send me your message that you listen my lecture. Goodbye.